In our final lecture of Chapter 2, we're going to discuss the nature of ions and molecules and how electrons play an important role in chemical behavior. We've talked about the nature of the makeup of an atom. Protons and neutrons are the particles that have considerable mass, so they contribute appreciably to the mass of an atom, while electrons are significantly smaller. But electrons play an important role. Electrons are actually what give an atom its reactivity. It is the interaction between electrons, between adjacent atoms, that cause the formation of chemical compounds. There are three types of electron interactions that can take place between atoms that are coming into chemical combination. The three types differ in the way that the electrons are exchanged. It depends upon the nature of the atoms themselves, and there are predictions that can be made based on the nature of the elements. If the two atoms that are interacting with one another are both metals, then the interaction that takes place is called a metallic interaction or a metallic bond. If the two atoms in question are both nonmetals, then the interaction is considered a covalent interaction or a covalent bond. Lastly, if we see an interaction taking place between a metal atom and a nonmetal atom, the result of that is what we call an ionic interaction or an ionic bond. Regardless of the nature of the atoms themselves, when electronic interactions take place, they do so following a particular rule. And the rule goes a little something like this. When entering into chemical combination, atoms tend to attempt to obtain the same number of electrons as the nearest noble gas. If you'll remember, those noble gases are the group 18 elements: helium, neon, argon, krypton, xenon, radon, and oganesson. Those elements that we find in the last vertical column on the right-hand side of the periodic table. We find that those noble gases are very unreactive gases. They do not tend to interact with anything. Well, there's a reason for that, and it lies in their electronic structure. Well, let's start to put some of the pieces of the puzzle together. If electrons are instrumental in chemical interactions, and these noble gases do not tend to interact chemically, then there must be something about their electron configuration that lends a certain sense of stability, so that they don't want to interact. They're already electronically happy, if you will. So when other atoms interact with one another, they tend to do so in an attempt to gain that electronic stability, the electronic stability that the noble gases offer. In the case of ionic bonding, where we see a metal interacting with a nonmetal, the exchange of electrons involves the gaining and losing of electrons. Metal atoms tend to lose electrons, while nonmetal atoms tend to gain those electrons. In the case of covalent bonding, we don't see a gaining and losing, we instead see a sharing of electrons. And finally, in the case of metallic bonding, we see an extreme form of electron sharing. Let's explore a very common ionic interaction, the interaction between an atom of sodium, a metal, element number 11 on the periodic table, and chlorine, a nonmetal, element number 17 on the periodic table. Now, based on their atomic numbers, we know that an atom of sodium has 11 protons and 11 electrons. An atom of chlorine has 17 protons as well as 17 electrons. If these two things are to interact, they're going to do so based on that rule. they're going to attempt to obtain the same number of electrons as the nearest noble gas. Sodium at element number 11 is closest to element number 10, neon. So if sodium is to interact with chlorine, it wants to lose one electron so that it has a total of 10 electrons, the same number of electrons as neon. Chlorine, on the other hand, with 17 electrons, is nearest argon, element number 18. So if chlorine is to participate in this interaction, it wants to gain one electron so that it has the same number of electrons as argon. Well, if you've got an atom that wants to lose one electron and an atom that wants to gain one electron, well, that kind of seems like a match made in heaven. But there's a problem. We can no longer call it an atom once it has gained an electron. We can no longer call it an atom once it has lost an electron. Remember, fundamentally, an atom must have the same number of protons as electrons. So with the gaining and the losing of electrons, we create a new entity. An entity that we call an ion. An ion is formed as a result of an atom gaining or losing one or more electrons. Now that there is an imbalance in the number of sources of positive charge, protons, and sources of negative charge, electrons, we can say that an ion carries a net positive or negative charge, depending on whether it has more protons than electrons or more electrons than protons. So what happens in the previous example? We see an atom of sodium losing one electron and becoming a sodium ion. Now, since that ion has one more proton than electron, the protons outweigh the electrons. With one more proton than electron, the sodium ion carries a charge of +1. The chlorine atom, with its 18 electrons, is no longer considered to be an atom. It is instead an ion. And since there are more electrons than protons, and specifically one more electron than protons, then this ion based on chlorine now carries a charge of -1. It is the interaction of a positively charged sodium ion and a negatively charged chlorine or chloride ion that is the ionic bond. Positively charged things are attracted to negatively charged things. The attraction, the interaction is the ionic bond. Metals tend to lose electrons, which means that they will have more protons than electrons when ions are formed. Nonmetals tend to gain electrons, which means that they will have more electrons than protons. Positively charged ions are called cations, while negatively charged ions are called anions. And if you look at the table at the bottom of this slide, you will see a listing of positively charged cations and negatively charged anions. You will notice that the charge on the ions can differ. Well, that's very much dependent upon the number of electrons that were either gained or lost in order to achieve that noble gas configuration. We looked at both the sodium cation and the chloride anion, but let's look further. Look at element number 20 on your periodic table. Element number 20 is calcium. An atom of calcium has 20 protons and 20 electrons. If calcium is to interact with a non-metal, It's going to do so in an attempt to walk away with the same number of electrons as the nearest noble gas. Well, at element number 20, the nearest noble gas is argon at element number 18. So if an atom of calcium is to ionize, if an atom of calcium is to form an ion, it is going to lose 2 electrons. That means that the ion will have 20 protons and only 18 electrons. Since it has 2 more sources of positive charge than negative charge, the charge on a calcium cation is +2. Similarly, if you look at aluminum, element number 13, element number 13 is nearest neon, element number 10, as opposed to argon, element number 18. So if aluminum is to ionize, it is going to lose 3 electrons, forming a cation with a charge of +3. If you look at the list of anions, you will see that in the same way that chlorine forms an ion with a charge of -1, so would bromine. Bromine, which is directly underneath chlorine on the periodic table at element number 35, needs 1 more electron to look like krypton. If it gains that 1 electron, then it forms the Br- ion, a bromine-based ion that carries a charge of -1. Oxygen at element number 8 is nearest neon, element number 10, in terms of noble gas configuration. So if oxygen is to interact with a metal, it's going to do so in an attempt to gain 2 electrons. If it has 10 electrons and 8 protons, then it will form an anion with a charge of -2. Ripped from your textbook, we find an image that speaks to some common ions that are formed from the elements themselves. Now, atop each group, you will see a designation of 1A, 2A, 3A, things of this nature. This is an archaic way of labeling the groups. Group 1A is group 1, group 2A is group 2, group 3A is 13, all the way to group 8A being group 18. So keep that in mind. But what we find are, based on that general rule, that idea that when entering into chemical combination, atoms will tend to obtain the same number of electrons as the nearest noble gas. We find that the elements that we find in group 1 tend to lose 1 electron to look like the noble gas that is just before them. So lithium, for example, at element number 3, is nearest helium, element number 2. So it's going to lose 1 electron. With 3 protons and 2 electrons, it now carries a charge of +1. Sodium, as we saw in the previous example, wants to lose 1 electron to look like neon. Potassium wants to lose 1 electron to look like argon. The elements in group 2 want to lose 2 electrons to achieve the same feat. Now, in doing so, they form a cation with a charge of +2. Now, the transition metals can get a little tricky. Sometimes they don't always obey that rule. Sometimes they lose more electrons, sometimes they lose fewer electrons than you would suspect. So for the time being, we're going to keep the transition metals on the back burner. But as we traverse the zigzag line into the realm of the nonmetals, we see the same behavior with anions that are formed. The halogens, things like fluorine and chlorine and bromine and iodine, are so close to having the same number of electrons as their nearest noble gas. They're just 1 electron shy. So in an interaction with a metal, it's going to want to gain one electron. Fluorine wants to gain one electron to look like neon. Chlorine wants to gain one electron to look like argon. Iodine wants to gain one electron to look like xenon. And these ions are referred to as monatomic because they come from one atom. The prefix mono meaning one, and the word atom. So when these substances are formed from the component ions, ions combine in order to form ionic compounds. And since compounds are electrically neutral, that means that they do not carry a charge. The charge has to balance out between the positive charge and the negative charge. So if we had an example of something like magnesium, magnesium tends to form a cation with a charge of +2. Nitrogen tends to form an anion with a charge of -3. That means that in an interaction between magnesium and nitrogen, magnesium wants to lose 2 electrons, nitrogen wants to gain 3. Well, they can't do that in a one-to-one fashion and everybody be happy. One magnesium isn't going to be enough to make one nitrogen happy. So in order to figure out the formula for the resulting compound, in other words, how many magnesiums and how many nitrogens does it take to make a neutral compound, we use the method that is illustrated here. We take the charge on the cation and make it the subscript of the anion. We take the charge of the anion and make it the subscript of the cation. And in this instance, it works out in a 3-to-2 fashion. 3 magnesiums are willing to give up enough electrons to make 2 nitrogens happy. 3 magnesiums will give up 2 electrons apiece, giving us a total of 6 electrons being lost. Each nitrogen is willing to gain 3 electrons, and since we have 2 nitrogens, then they are willing to gain 6 electrons. So everything works out nice and neat. Now, if it turns out that the subscripts after you do this are not in the lowest whole number ratio, then you need to divide them by the greatest common factor. For example, an atom of sulfur interacting with an atom of calcium. Calcium is going to form an ion with a charge of +2. Sulfur is going to form an ion with a charge of -2. Well, it's obvious that they have enough electrons to make each other happy. Calcium loses 2, sulfur gains 2. But if you were to use this protocol, you would have a formula of Ca2S2. Well, since both of those subscripts are not in the lowest whole number ratio, you can simply divide them by 2 and get the formula of CaS, 1 calcium per sulfur. Now, I wouldn't have introduced the concept of monatomic ions if there weren't something contrary to that. Sometimes, rather than a single atom gaining or losing electrons, we find a group of atoms, a cluster of atoms that will gain or lose electrons. These are called polyatomic ions. An example of a polyatomic cation is the ammonium cation. It has the formula of NH4+. That means that a cluster of atoms, including 1 nitrogen and 4 hydrogens, have combined and lost an electron. An example of a polyatomic anion is the sulfate anion, in which we see 1 atom of sulfur and 4 atoms of oxygen combining and gaining 2 electrons. Now, right now, it's not your concern to understand how that happens, all right? All you need to know is that it does happen, and be able to recognize it when you see it. Now, there's a list of polyatomic ions that I'm going to send you via email. Typically, this is a list that I would have you learn piece by piece. I'm going to highlight the ones that I'm going to hold you responsible for in intervals. I'm going to start you off with 7, and then I'm going to add 5 more, and then I'm going to add 5 more. There are more than 17 on the list in total, but we got to crawl before we walk. Covalent bonding exists when a pair of electrons is shared by 2 atoms. A covalent bond will form between 2 atoms of chlorine, each of which have 17 electrons. Well, neither wants to lose an electron to the other. So in the nature of a chlorine-chlorine interaction, imagine if each chlorine holds out 1 electron for the other chlorine to share. So while each has 17 electrons of its own, if 1 electron is shared from the other chlorine, then it appears to have 18 electrons, similar to the electron configuration of an atom of argon. So in a covalent bond, the electrons do not belong to an individual atom, but are instead shared between 2 different atoms. The nature of metallic bonding involves an extreme case of sharing, and while I would love to go into great detail about the nature of metallic bonding, it is a very complex model, a model known as the electron C model, which goes beyond the scope of this class. So simply based on metallic or non-metallic behavior, we can predict whether 2 elements will form covalent bonds, ionic bonds, or metallic bonds. Phosphorus and chlorine. Phosphorus and chlorine are both nonmetals, elements 15 and 17 respectively. So a nonmetal-nonmetal interaction results in covalent bonding. Carbon and oxygen, similarly, both nonmetals. When they combine, it is a result of covalent bonding. Sodium and chlorine, as we saw in the previous example, are a result of a metal interacting with a nonmetal, resulting in ionic bonding. Copper and sulfur, similarly, are going to result in ionic bonding. While things like gold and silver interact metallically, copper and tin interact metallically. Now, it should be noted that when it comes to those noble gases, we do not see any bonding taking place. Neon will not bond with copper. Argon will not bond with hydrogen. Xenon will not bond with much of anything. Okay. These interactions result in the formation of chemical compounds. A compound is a pure substance made up of 2 or more elements chemically bonded in a definite proportion by mass. Some examples of chemical compounds are carbon dioxide, hydrogen peroxide, aspirin, and simply water. The chemical makeup of a compound is given by its chemical formula. That basically tells us what elements are present in a compound and how many atoms of each element are present. And that is represented as a subscript, a tiny little number written after each element. If there is no number, then it is assumed that there's only 1 atom in the chemical formula. So as we see below, carbon monoxide has a chemical formula of CO, suggesting that there's 1 atom of carbon and 1 atom of oxygen and a molecule of carbon monoxide. Carbon dioxide, on the other hand, has 1 atom of carbon and 2 atoms of oxygen. Water, with the chemical formula of H2O, is made up of 2 atoms of hydrogen and 1 atom of oxygen. Now we can classify compounds based on the number of elements that it takes to make up the compound. Substances that are made up of 2 elements are called binary compounds. Substances that are made up of 3 elements are called ternary compounds. Substances that are made up of 4 elements are called quaternary compounds. And we could go on and on and on and on, but I choose not to. These are some examples of binary compounds. Octane is a binary compound with the chemical formula of C8H18, 8 atoms of carbon and 18 atoms of hydrogen chemically combine to form a molecule of octane. Carbon dioxide is made up of carbon and oxygen. Sodium chloride is made up of sodium and chlorine. And lastly, water is made up of hydrogen and oxygen. Some examples of ternary compounds: sulfuric acid, which is a combination of hydrogen, sulfur, and oxygen. Nicotine, which is made up of carbon, hydrogen, and nitrogen. Potassium nitrate, a common fertilizer, which is made up of potassium, nitrogen, and oxygen. And the anti-inflammatory analgesic known as ibuprofen is made up of carbon, hydrogen, and oxygen. Finally, we see a listing of quaternary compounds: caffeine, acetaminophen, also known by the trade name Tylenol, bismuth subsalicylate, which is the active ingredient in Pepto-Bismol, and adrenaline, also known as epinephrine. You will notice that each of these compounds is made up of 4 elements. Now, of all of the elements listed on the periodic table, only 7 of them occur in nature as what we call diatomic molecules. These are molecules that are made up of the element themselves in 2 atoms joined together, hence the term diatomic. Those 7 elements are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Now, I don't have a mnemonic device, so an easy way to memorize these. I'm sure that if you tried to put your thinking caps on, you could figure out a sentence that was 7 words long, that was HNOFCBI. Who knows, maybe I'll ask you about your favorite one before it's all said and done. Now, I spoke of chemical formulas. Chemical formulas are a way of relaying the information with regards to what elements are present and in what amounts. But there are different types of chemical formulas. There's the empirical formula. Now, the empirical formula of a substance gives the lowest whole number ratio of atoms of each element in a compound. So, for example, if we have a molecule of glucose, which has the chemical formula of C6H12O6, a molecule of glucose is made up of 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. In the simplest whole number ratio, you can essentially divide all those numbers by 6, leaving you with an empirical formula of CH2O, meaning that for every 1 carbon, you have twice as many atoms of hydrogen, and for 1 carbon, you have just as many atoms of oxygen. So looking back at the original formula, we see that that is indeed true. We have twice as much hydrogen as we have carbon, and we have the same number of oxygen atoms as we have carbon atoms. So the simplest whole number ratio gives you the empirical formula. Now, you may ask, why is the empirical formula important? Well, right now it's not, but by the time we get to chapter 3, it's going to be pretty darn important. The molecular formula, what we refer to as the true molecular formula, gives the exact number of atoms of each element in a compound. So for glucose, the true molecular formula is C6H12O6, telling you exactly what's there and how much of it is there. Now, if we know the molecular formula of a compound, we can determine its empirical formula. Now, doing the reverse, that's something that we're going to find in chapter 2. And it's something that's going to be very important in doing chemical determinations. Lastly, we find a structural formula. Now, a structural formula gives graphical information. It shows you how the atoms are connected to one another. In a molecule of glucose, that is 6 carbons, 12 hydrogens, and 6 oxygens, without a structural formula, you don't know what's connected to what. All right. So here on this slide, we see a molecule of methane gas, which we call natural gas. It has the chemical formula of CH4. Its structural formula shows that there's a carbon that is connected to 4 hydrogens. The hydrogens aren't connected to each other. They are all connected to the carbon. The last thing we're going to do in this chapter is understand how to name compounds. Compounds, whether they be molecular compounds or ionic compounds. Now, we're going to easily be able to name ionic compounds. There are general rules, and there are rules for naming certain types of molecular compounds, specifically binary molecular compounds, those compounds that are made up of 2 different elements. If we have a ternary compound or a quaternary compound, well, things get a little tricky. There's not really a common naming scheme for those, but we should be able to name these 2 types of compounds. When naming ionic compounds, it's simple. First, you write the name of the cation, and then you write the name of the anion. That's it. Now, if the cation is a monatomic ion that follows those general rules, those general trends, then it's simply the name of the atom. Sodium forms the sodium cation. Potassium forms the potassium cation. Calcium forms a calcium cation. So the name of the cation is simply the name of the element itself. Now, there are some cations that can get a little tricky. For example, you'll remember that we kind of glossed over those transition metals in that graphic a few slides back. The transition metals were empty. So we weren't able to determine the charge of a transition metal when it becomes an ion. Well, that's because for many of these elements, multiple charges can be formed. And once again, it's not our duty to understand how it happens or why it happens, just to recognize that it does happen. Copper at element number 29 can form 2 possible ions, copper +1 and copper +2, suggesting that copper will lose either 1 electron or 2 electrons when it ionizes. Well, in order to differentiate between those 2, we would call the first one copper 1 and the second one copper 2, because that is the number of electrons that has been lost. Hence, that is the positive charge associated with each ion. Titanium, element number 22, is another example of a metal that can achieve multiple ionic states. Titanium +2 involves losing 2 electrons, while titanium plus 4 involves losing 4 electrons. So we would refer to these as titanium 2 and titanium 4 when it comes to naming a compound. The anion, if it is simply an element, we drop the ending and add IDE. So when fluorine becomes an ion, it becomes the fluoride ion. When nitrogen becomes an ion, it becomes the nitride ion. When oxygen forms an ion, it becomes the oxide ion. And since there are only a handful of nonmetals, if you look to the right side of the zigzag line, there are only about 20 or so nonmetals, and well, let's face it, 7 of those are noble gases, and they're not going to form an ion of any type. Then that whole idea of dropping the ending, you don't have a lot of endings to choose from. All right, so it's not, hopefully, going to be that complicated. If the ions in question are polyatomic ions, then simply write the names of the polyatomic ions. So when sodium interacts with chlorine, the resulting compound is called sodium chloride. When calcium reacts with sulfur, the resulting compound is calcium sulfide. When copper interacts with oxygen, it can form one of 2 compounds, depending on whether or not the copper atom loses 1 electron or loses 2 electrons. Now, if it loses 2 electrons, the oxygen is willing to take on those 2 electrons, so they will exist in a 1-to-1 fashion. That will result in what we call copper 2 oxide. If instead the copper loses only 1 electron, then we're going to need 2 of those copper 1 ions in order to interact with the oxygen. So that would be copper 1 oxide. When naming binary molecular compounds, well, once again, there are a series of rules. We take the 2 elements in question, both nonmetals. The name of the element farther to the left on the periodic table is usually listed first. So in the case of something like carbon and oxygen, since carbon is closer to the left-hand side, then carbon would be listed first. And there are a series of Greek prefixes that are going to be used to indicate the number of atoms of each element. So if we have a molecule of a binary molecular compound made up of carbon and oxygen that is made up of 1 atom of carbon and 2 atoms of oxygen, then that compound would be called carbon dioxide. Notice the prefix that is used is always used with the second element, and most of the time is used with the first element. Now, in the case of mono, we do not use mono with the first element, so we wouldn't call it monocarbon dioxide. We'd simply call it carbon dioxide. And as I prematurely suggested a moment ago, the ending on the second element is going to be dropped and changed to IDE. So indeed, we would have carbon dioxide. A carbon interacting with 4 chlorines is going to form carbon tetrachloride. The prefix for 4 is tetra. Now, if the prefix in question on the previous slide ends with an A or an O, and the name of the element begins with a vowel, then the 2 vowels together are combined into 1. We essentially drop that A or O so that we don't have something like monooxide or pentaoxide. So in the case of N2O5, a compound that is made up of 2 nitrogens and 5 oxygens, we would call it dinitrogen pentoxide. In the case of a molecule where we see one atom of carbon and one atom of oxygen, we would call that carbon monoxide. One carbon, one oxygen, carbon monoxide. I want to thank you for your time. At the end of this chapter, there is a section on organic molecules. We're going to bypass that for the time being. Perhaps in the future we will revisit it, but for the time being, it's going to get left on the cutting room floor. I want to thank you for your time. I know this was a little longer lecture than typical, but there's a lot of information that needed to be presented. Thank you, and good luck learning all of this stuff. Take care.